I posted a limits worksheet on Canvas, and now I want to go over the solutions on how to find each one because they're very similar in nature. Now, the first problem we want to look at is the limit as x goes to 4 of 2x squared minus 2x minus 12 over x minus 3. Now, there's a tendency to use all sorts of limit techniques and to evaluate and do things that aren't necessary right off the bat. What we always want to do is ask the question, can we simply evaluate the function at 4? And in this case, we can because it's not an indeterminate form. So if I simply replace numerator and denominator with the number 4, my numerator will be 2 times 4 squared minus 2 times 4 minus 12, which is 12. My denominator will be 1. So this isn't anything special. I can evaluate this directly and just say the limit is 12. Okay, that's it. Now, what if I change this to 3? Now I can't evaluate this directly because now numerator and denominator will both tend to 0. And this is the notation that we generally use. We'll say approaches the form 0 over 0. We use the brackets to indicate this is not a value, this is a form. This is what is called an indeterminate form, which means that the problem at the very least is interesting, and probably my strategy will be to factor and cancel. That's the majority of the time we have this form. Now, if the numerator and denominator both tend to that form, we know from the fundamental theorem of algebra that since x equals 3 makes the numerator and denominator equal to 0, then x minus 3 has to be a factor of both. So my numerator will factor simply to x minus 3 and then 2x plus 4. That's easily seen right there. And so if I do that factorization, I can now cancel the factors. Now remember, the limit is where it's going, not the functional value. Those are not exactly the same thing. In the previous example, the limit and the functional value were the same thing because there was nothing strange happening at 4. In this case, x equals 3 is not in the domain, so f of 3 does not actually exist. But as x approaches 3, I am approaching 2 times 3 plus 4. Therefore, my limit is 10. And this is very simple to evaluate. I cannot evaluate this quantity because it's an indeterminate form, but after I factor and cancel, I can evaluate what's left. Now let's keep going. Okay, in the next case, we've got the limit as y goes to 2 of 3y cubed minus 5y squared minus 4 over 3y squared minus 8y plus 4. I always want to know if I can evaluate this directly. So if I replace numerator and denominator with the number 2, once again, I will see that 3 times 2 cubed minus 5 times 2 squared minus 4, that is 0. Now, if my denominator were not approaching 0, then this is a very easy limit to evaluate. My answer would just simply be 0 because 0 over a number is 0. But in this case, the denominator is also approaching 0, which again means this is an interesting problem to say the least. It also means that I'm guaranteed that y minus 2 is a factor of both numerator and denominator. I know my denominator looks like this. I know my numerator looks like this. This one's not too hard because this is quadratic. I can easily see that's going to be 3y minus 2. But on top, that's a cubic. That's a little bit harder to factor. So what we'll do is use our synthetic division and use a root of 2. So if I use a root of 2, now remember, write all the coefficients in descending order. So 3, negative 5, there is no y term, so 0, negative 4. And then I bring down the first term, 2 times 3. Then I add the terms, 2 times 1, then I add the terms, 2 times 2, then I add the terms, and of course, that is my remainder. That means that y minus 2 was in fact a factor, so in reverse, this is the constant, the linear, the quadratic. So that would be 3y squared plus y plus 2. So at this point, I have factored numerator and denominator. Now, y equals 2 is not in the domain of this function, but after I factor and cancel, I should get a quantity where y equals 2 isn't a problem. You see, my denominator will no longer approach 0, and my numerator will take on this form. Now, this quantity here is always equal to this quantity here, except at y equal 2, because y equal 2 is not in the domain. The limit is not what's happening at y equals 2, it's what's happening as I get closer and closer and closer to y equals 2. So as I'm getting closer to y equals 2, my numerator is getting closer to 3 times 2 squared plus 2 plus 2, which is 16. My denominator is getting closer to 3 times 2 minus 2, which is 4. So my limit is simply 4. Another way to think about that is that if I were to sketch this graph or do this with my graphing calculator or using Desmos, there would be a hole at the where when y is 2 and the functional value is 4, there would be a hole there, okay? But the function would be going in both directions on both sides. Interesting concept. All right, let's keep going. Now, the way we write limits is very, very important that we are consistent and that what we say is exactly what we mean to say. You notice that I do not drop the limit expression until I've evaluated the limit. So in this case here, now I have something that's not quite as simple to work with. I have something that is not a quotient of polynomials. This is not a rational function. But as z approaches 9, my numerator again tends towards 0. I like that. But as z approaches 9, my denominator also tends towards 0, square root of 9 minus 3. So once again, I have the indeterminate form 0 over 0, but I cannot simply factor and cancel because that's not a polynomial. So what can I do? Well, probably the simplest thing is I would like to remove z minus 9 from the problem. If I could remove that from the problem, then this would be easy to evaluate. So if I can create a z minus 9 in the denominator, I'd be able to factor and cancel. And the way I will do that is to multiply top and bottom by the conjugate of the denominator. So essentially, I'm multiplying by 1. And in fact, there are no problems here because as z approaches 9, root z plus 3 is approaching 6. So in a sense, I'm kind of multiplying numerator and denominator by 6, or by numbers that at least are approaching 6. But when I do this step, my denominator will then be, remember, a minus b times a plus b is a squared minus b squared. So my denominator will simply be z minus 9. My numerator is z minus 9 times root z plus 3. I do not want to distribute in this case because I can clearly cancel these factors. So this would leave me with the limit as z approaches 9 of the square root of z plus 3. And that's very nice because I can evaluate this expression. So square root of 9 plus 3, that would simply be 6. And what makes this nice is this was not a rational function, but we still had a factor and cancel scenario by using the conjugate. Okay, so far, we've used essentially the same technique each time. We factored and canceled the term that was causing the denominator to go to 0, which is usually what you can do when you have this type of indeterminate form. Okay, next problem. I have the limit as x approaches a of x to the 4th minus a to the 4th over x minus a. Now, a can be any real number. But in this case here, you notice if x is approaching a, my numerator is approaching a to the fourth minus a to the fourth. And my denominator is approaching a minus a. So once again, I have the form 0 over 0. And clearly I can factor, except, oh, that numerator is a fourth degree polynomial, and a isn't a specific value. So using synthetic division in this case might be a little bit tricky. But we also notice that the numerator is a difference of squares. So if I treat it like this is basically x squared squared minus a squared squared. So I can think of this as being a difference of squares. X squared being squared minus a squared being squared. So this would factor as x squared plus a squared times x squared minus a squared. And then I also notice that this guy's a difference of squares. So I can continue and write this as x squared plus a squared, x plus a, x minus a. And I finally have my factor of x minus a. So I can rewrite this limit as the limit as x approaches a of. Now this would be my numerator, x squared plus a squared, x plus a, x minus a, all over x minus a. Now, I cannot evaluate it yet, but when I remove the problem, which is the x minus a term, I should get something that I can easily evaluate. So at this point here, after I cancel the common factors, and you notice I cannot evaluate yet because it is still of the form 0 over 0 if I try to evaluate, but I'm going to remove the problem. So this is x squared plus a squared, x plus a, because I canceled those factors, and this can easily be evaluated. If I allow x to approach a, this is going to approach a squared plus a squared, which is 2a squared, times a plus a, which is 2a, so this gives me 4 times a cubed. And that would be true for any value I used for a. Okay? This one was a little trickier because I didn't give you a specific number. Now let's continue. Next one. Algebraically, this is probably one of the more challenging ones. The limit as a approaches 0 of 1 over x plus a minus 1 over x all over a. And again, we see this common theme of an indeterminate form. This one's not as obvious. In this case, clearly my denominator is approaching 0, which obviously is a problem. And as a approaches 0, my numerator approaches 1 over x minus 1 over x, which is also 0. So this is the indeterminate form 0 over 0, which means ultimately I should be able to factor and cancel, except that numerator does not look very friendly. Now, we've looked at problems like this before. In the review of algebra that I posted, we did something similar to this. I have 2 quotients on top, and the common denominator of those 2 quotients would simply be the product of x plus a and x. So if I multiply numerator and denominator by the quantity x plus a times x, I'm multiplying top and bottom by 1. And as a approaches 0, that's still not a problem. But when I do this, I should be able to create a rational expression that I may be able to work with. So now my denominator, I'll do that first, that's the easier of the two, that's a times x plus a times x. My numerator, when I multiply this by this quantity, the x plus a is canceled, leaving me just an x. When I multiply this by this quantity, the x cancels, leaving me x plus a. Now you notice on top, if I go ahead and distribute that negative, I'm going to get the limit as a approaches 0 of, now my denominator is not going to change, but I'm going to have x minus the quantity x plus a, which leaves me simply with negative a. A being the problem child here, and I can cancel the a's this time. So that leaves me the limit as a approaches 0 of -1 over x plus a times x. Now, as a approaches 0, this is not a problem. My denominator will approach x times x, and so my limit is -1 over x squared. Now, notice my limit is not a value. My limit is a function. And in fact, as we're going to find, the further we go in calculus, limits are rarely going to be numbers. Limits are usually going to be functions. Up till now, we've only been dealing with the simplest type, the type we can evaluate directly. But in this case, I got a function, and so the algebra allowed me to get there. Any path I took, no matter how long it took me to manipulate this, I was eventually going to get something that looks like this. We just want to get there faster if we can. All right. Now, one of the things we know about limits are if it's possible that the limit from one direction is different than the limit from another direction, the limit may not exist. One of the rules that we have, very, very critical rule, is if I have a one-sided limit, this means the limit as I approach a number from values less than that number. And then I have potentially the same situation, but I'm approaching from numbers bigger than that number. These things have to be equal for the limit to exist. Now, this hasn't been an issue up till now because the only problem we had was the potential that the denominator was 0. It didn't change what my limits were going to be from the left or from the right. But if I have what is called a piecewise function, a function that has different definitions from left and right, from one direction it's one function, from another direction it's a different function, now I have to consider one-sided limits. So let's consider the absolute value function. That's a very, very interesting function. The absolute value of x. So if I were to draw that graphically, which sometimes is very useful, looks like this. On this side, it's the line y equal x. On this side, it's the line y equals -x. So we say this is equal to x or -x. It's x when x is greater than or equal to 0. It's -x when x is less than 0. So the absolute value function is what is called a piecewise function because there's no way I can write it as just one of these. I have two different functions going on. And the limit of the absolute value is not really an issue. But what if we considered the following? I want the limit as x approaches 0 of the absolute value of x over x. Ooh, now this is a totally different animal because I clearly have an indeterminate form 0 over 0, but I have an indeterminate form in a piecewise function. So this means I have to consider the two one-sided limits. So we'll start by doing the limit from the left and then the limit from the right. So the limit as x approaches 0 from the left. Oops. All that means when I say that is I am approaching from values that are less than 0 in this case. Now, when x is less than, when x is less than 0, then the absolute value graph actually looks like this. So this would equal -x over x. You see, you cannot evaluate while the absolute value is there because I can't do any type of algebra. But -x over x, this is still an indeterminate form, but those cancel. And those would leave me with the limit of -1. And we know that the limit of a constant is a constant. So that limit is, in fact, -1. So the limit from the left is equal to -1. Now let's consider the limit from the right. So if I do the limit as x approaches 0 from the right of absolute value of x over x, now I'm approaching it along this curve. That means that this would be the limit as x approaches 0 from the right of just simply x over x. And if it's just simply x over x, then that's the limit as x approaches 0 from the right of the number 1, which of course would simply be 1. Now we have a problem because the limit from the left was -1. The limit from the right was +1, and those are not equal. That means my original statement of the limit as the absolute value of x over x as x approaches 0, that limit does not exist. I'm going to write right here. That's what we call a DNE. Does not exist because the limit from the left and the limit from the right were different values. Graphically, what that means is that this graph would have looked like this. As I approached 0 from the left, that quotient was always equal to -1. As I approached 0 from the right, that quotient was always equal to +1. The quotient does not exist at 0, but I got two different limits. Okay. Now, graphs are sometimes very useful to explain what's going on, but you can't use a graph to determine your limit in general, because most of the time the graph will be more complicated than the actual taking of the limit would be. Plus, if you're trying to do a graph and you have, let's say, a removable discontinuity, a hole, it's not going to actually show up on your picture if you use technology because it's only one point. So we want to be able to do the algebra to make sure. Now let's look at a different type of piecewise function. Okay, let's consider the following. Let's consider f of x equals x squared when x is negative, the number 4 when x equals 0, and x when x is positive. So it looks like y equals x squared to the left of 0, looks like y equals x to the right of 0, and the number 4 when x is 0. Graphically, this is very simple to represent. So graphically, to the left of 0, it looked like y equals x squared. To the right of 0, it looked like y equals x, but it's not defined at 0, or at least it's not defined between those two. So I have a hole there because it's 4 when I am 0. So I am this until I get to 0, it jumps up to here, and then on the right side, it looks like this. So this would be the graph. Now, you wouldn't be able to do this on a graphing calculator or using technology because trying to do a piecewise function actually isn't going to work particularly well, especially when you have the one point there. Now, I'm asking here, what is the limit as x approaches 0 of f of x? Because that really is the only interesting question. If I used any number other than 0, if I used any negative number, then all I'd have to do is just plug it into here. If I used any positive number, I just have to plug it into here. But I'm using 0, which it's different from each direction. So in this case, again, I'll have to do the one-sided limits. So let's start with the limit from the left. So the limit as x approaches 0 from the left of f of x is the limit as x approaches 0 from the left of the function y equals x squared. And clearly that limit would be 0. Okay, in fact, that's easy to see on my graph. That's where I was headed. I was headed to the origin. Never got there, but I was headed there. So as x approaches 0 from the right of f of x, that means I'm approaching 0 along this path. I'm going this direction, and that would be on the function y equals x. And again, as x approaches 0 on the function y equals x, that limit is 0. Now notice the limit from the left and the limit from the right are in fact equal. Therefore, the limit exists and the limit is 0. Now, this is a little bit confounding. The limit is 0, but the functional value is 4. The functional value and the limit are different animals. Okay, the limit is where as I'm heading, the functional value is where am I at that point. And because both of these are approaching the origin, that means the limit is the origin. Okay, so hopefully this helps you because these are the types of limits we start early. We're going to do all sorts of different types as the course goes on.